So today we're going to look at the rules for drawing rays on a ray diagram to identify the location that an image will be formed at on a convex lens. To start out, we need to understand a couple of vocabulary pieces. So when we look at our lens diagrams, we're going to see the actual convex lens itself. And convex just means that it has that curve that bulges outward. We'll also see a straight line that goes through the center of that lens on the horizontal. And this is going to be representing our optical axis. And then we'll also see two dots, one on either side of the lens. These dots are going to be equal distance from the lens, and they're going to be called the focal point of that lens. And what this means is if we had light that came from a distant object like the sun, and all of that light, as it goes through that lens, will be focused to that specific point. If you've ever seen movies, or maybe as a kid you played with a magnifying glass, this is the point where you're able to focus all that solar energy to harness it in order to make a fire, or burn ants, or whatever it is that you've seen them do. So that focal point is where all of that energy can be focused based on the curvature of the lens. And again, so I have a focal point on the front side in case the light comes in from the right, and I have a focal point on the left side for when it comes in from the other side. So both points are called focal points. They are going to be the same distance from the lens regardless of which side that we're on. So if this was 3 centimeters, then my other dot over here would also need to be 3 centimeters. And the distance that this focal point is going to be based off of this curvature of the actual lens itself. And we're going to be using these focal points as a reference tool when we start drawing our diagrams. So for the diagrams themselves, we have 3 rules that we are going to follow in the process of drawing these rays. Okay. Now you have 3 rules. The reality of it is you only need to be able to draw 2 rules at a time, but I definitely suggest drawing all 3 in case you are off on one of those lines. It'll reduce your error long term. So the first rule that we have is going to start out parallel to that optical axis, and then once it hits the lens, it's going to refract through the focal point. Now remember that it's the lens that causes it to refract, so this is not going to happen until it gets to that center point of the lens. Sometimes I even tell my kids to draw kind of a vertical line to represent that center point to make it easier to identify when to make all these changes start to occur. So again, if you were to draw this, I would start at the very tip of my arrow, and I would go as straight as I can until I get to that center point of the lens, and once I get there, now my line is going to shift. Still going to be a straight line, but it's no longer going to be traveling parallel to the axis. Now it's traveling so that it goes through that focal point on the far side. My second rule says that if the ray goes through the first focus, then after it hits the lens, it will refract and go parallel to the axis. So we see that pictured here. It's going to go through that first focal point here. Once it gets to that lens, now it's going to be refracted and bent, and it will change direction and go parallel to that axis on the other side. And then the final rule is that light that travels straight through a medium with no angle doesn't actually refract or bend. So if I had water and I sent light through and at some angle from the normal, then it would be guaranteed to bend and shift. But if I sent that light directly straight down through the water at a perfect 90 degrees, then it would be unaffected by the water because there's no angle for it to be directed off of. So we see that same thing hold true when we get to our rules here. If we were to go directly through the center of the lens, then I'm going to be essentially matching the angle of the curvature of the lens, which means that it's not going to bend or shift or change position. So again, I'm going to start at the very tip top of my arrow, and I'm going to draw that line that goes directly through that center point of the lens, straight through without changing it at all. So now if I were to take all of these different lines that I've drawn and start to combine them together, I would be able to identify the location of my new image that's being formed. So for the purposes of this demonstration, and we're going to end up drawing a couple of others, if I were to start to look at where these lines are going to start to come together, let's see if I can do this. So just to kind of visualize, if I could take this second line that I drew and bring it up so that I line it up on top of my other lens, and I'm going to see that in this corner point at the end, that's where all my lines are going to come together. So I did the same thing with this one over here, and again, if I were to set it directly on top, then right at this point over here is where I'd start to see them come together. So the image that's produced by this position of the object and this position of the lens would form a new image over here. So I'm going to match my lines. My line started out at the very tip of the arrow, and my bottom of the arrow was placed on the optical axis. So that's what I'm going to have drawn here as well. So the bottom of my arrow is on the optical axis, and then the tip of my arrow is pointing to where those lines meet. So that's going to help me to decide that where my lines came together above the axis on this picture, they're below the axis over here. So my arrow is pointing up on the left side, and it's pointing down on the right side. That's going to let me know that my image is inverted. If my image is inverted, then I know that it's going to be considered a real image based off of our notes that we've already covered. I can also start to compare the height or the of each of these arrows. So looking at the height of these arrows, in this picture I can see that these are roughly the same height, so in this case they'd be about the same size. Or this would be an unmagnified image. So we're going to go ahead and take this over and use another sheet that we've got to do a couple of practice problems and see where that lands us. So here I've got my first image. Just like before, I've got 3 lines that I'm going to draw. So the first line that I'm going to draw is going to start out at the tip of the arrow. I'm going to go parallel to the axis, so as straight as I can make it. And when I get to that center point of the lens, now I'm going to stop, and I'm going to change position. I'm going to bend and refract through the far focal point. My second line is going to be the opposite. Starting at the arrow, I'm going to go through that first focal point until I get to the lens. And then once I get to that kind of midline of the lens, I'm going to refract and bend and now go parallel. So I can already see where my lines are coming together. Like I said, you only have to draw 2 lines, but just to make sure that I was 100% parallel, that I didn't miss a point, I like that third one. So I'm going to start at the very tip of my lens, and this time I'm going to go as straight through the very center as I possibly can, kind of imagining where the origin inside this lens would be. So all of my lines have come together over here. If I were to draw out what my new image looks like, again, I start off with the bottom of my arrow on the axis here, and then the tip of my arrow pointing to where all those lines converge. So I'm going to point to here. So here I have a lens going up. Here I have my lens pointing down. So I would consider this to be an inverted image. This is going to represent my object. It was the initial thing that was already physically there. And over here, this represents my image, that new thing that we produced as a result of the refraction through the lens. As soon as I see that it's inverted, I know for a fact that it's real. I also want to make a judgment of what happens to the magnification. So is it smaller, larger, the same size, or is it no image? Well, we know it's not no image because I was able to see my lines come together. Comparing the height of this one to the height of this one, and I can even get out my ruler and measure it, those look pretty close to being the same size. So I have roughly the same size for my image. This would be an unmagnified image. The last thing that we're going to look at is a lens equation. And the equation for solving with lenses is written 2 ways. 1 over the focal length equals 1 over the object distance plus 1 over the image distance, or if you're not a fraction person, you can use the inverse functions off of a calculator. So the inverse of the focal length is going to be equal to the inverse of the object distance plus the inverse of the image distance. So what do I mean by these distances? So from the object to the lens, that's going to represent my object distance. So my object distance is going to be the distance from the object to the lens. Whereas the image distance is going to be the distance from the lens to the image. And I can get that simply by measuring. So if I pull out a ruler and I do just a quick check on this, the numbers are already there in the box for us. So from the object to the lens is about 6 centimeters. And from that focal dot to the lens, this one's at 3, this one's at 6, so that'd be a difference of 3 centimeters. So the F, or the focal length, that's going to be representing how far it is from the dot to that lens. And again, you can measure that on either side, and you get the same answer. So now that I have these values, I could solve and figure out where my image was supposed to occur, and I could measure and figure out how close I actually got. So the way that this equation works, I'm going to do 3 to the negative 1, that's my focal length, 6 to the negative 1, that's the object distance, and we're going to be solving for the image distance. So, doing a little bit of algebra, rather than adding the inverse of 6, I'm going to subtract it. So now I have 3 to the negative 1 minus 6 to the negative 1 is going to give me my image distance to the negative 1. Grab a calculator real quick. And when I type this in my calculator, I'm going to come out with a decimal value, 0.16 repeating. Now I have an inverse function on this side, so I need to take care of that. I'm going to take the inverse of my answer, and that's going to help to get rid of this. So I'm going to take the inverse of both sides in order to cancel them out. So 0.16 repeating with that inverse function again, so I can take the inverse of my answer, and I'm going to hit equals in my calculator, and that's going to give me 6. So 6 centimeters is going to be my image distance. Alright, let's try another couple. So again, to start out, I'm going to draw in my rays. So my first ray is going to start at the top of the arrow, run parallel to the axis until it hits the lens, and once it hits the lens, it's going to refract and go through that far focal point. My next one is going to start at the tip of the arrow, and it needs to go through the near focus. Well, in this case, my arrow is on my focus, so if I started at the tip of my arrow and I went through the near focus, I'd end up with a totally vertical line. Well, let's try doing the third one to see if that helps us. So I'm going to start at the tip of my arrow, and I'm going to go through the very center of that lens. Well, I still don't have any crossing. And if I look at those lines that I just drew, these look to be pretty much parallel. I don't think that even if I had a paper that was a mile long, they would actually end up ever meeting. Well, this is a rule. As a rule, when the object is located at the focal point, then it does not work. There will be no image formed. If we try to start doing the math with that, we're going to see the same thing holds true. So I'm going to do the inverse of my focal length, set that equal to the inverse of my object distance, and solving for my image, well, if I took 3 to the negative 1 and I subtract it from this side, and 3 to the negative 1 and subtract it from this side, I end up with my image distance, even though it's an inverse, being 0. And if I took the inverse of 0, I still get 0. So this is going to, again, any time that the object is located at the focal point, will automatically provide us with no image. So I can't say that it's upright or inverted. I can't say that it's real or virtual. It's not present. So let's try the last picture that we have here as an example. And I wrote mine backwards. It really doesn't matter over here which way you do it because it's an addition factor, so either way will work just fine. Alright, so on our bottom one, again, same three rules. I'm going to start at the tip of my lens. I'm going to go through, straight across, parallel to the axis until I get to the lens, and then I'm going to bend and shift through that far focal point. My second line is going to be a challenge to draw. In order to draw this one, I would really need my lens to be quite a bit bigger than it actually is. So just to help you visualize it, I'm going to go from that focal point, and I need to cross across the very tip of that lens. So my lens would have to be, across the very tip of the arrow. My lens would need to be a lot taller. But once I get there, it would refract and go parallel. Now, since that one's a little funky to draw, I'm just going to see if the third one's a little bit easier to draw. So if I start at the tip of my arrow and I go through that kind of origin of the axis, then I can have my third line pretty easily. So now looking at this one, I don't see them coming together over here. But I can also see that over here, it appears as though they are separating. They're scattering. Which means, logically, that over here somewhere, they might come back together. So, I'm going to take my ruler and I'm going to extend these lines just a little bit further, but in the opposite direction to see what happens. So if I were to follow this line and bring it backwards, same thing. I'm going to follow this new line, bring it backwards, and follow my line and bring it backwards. So essentially I'm seeing what the reflection of that refracted ray would look like. And last week when we drew the ray diagrams, we were able to see that as something, the same objects that refract are also going to have the ability to reflect. So we're building off of that idea. Well, now I can see that my lines do come together. They come together up here. Just like before, my arrow should point to where those lines converge. So pointing to where my lines converge, tying it back down to the optical axis, this is going to be my image. Comparing it to that initial object, I can see that they're both pointing up. So this would be considered upright, which would mean that it's virtual image. Comparing the size, this one is almost twice as tall. So this would be a magnified image. It would be quite a bit larger. And then practicing that equation, solving it out to see how close I actually get, I'm going to do my equation. So the inverse of the focal point set equal to the inverse of the object distance and the inverse of the image distance. Subtracting this side. Grabbing my calculator. And now I get negative 0.16 repeating. And again, I need to take the inverse of both sides in order to cancel it out over here. So the inverse of that answer would be negative 6 centimeters. A negative is going to refer to a virtual image. Anytime that I have to measure backwards in the opposite direction of where I typically would, I'm going down the negative direction of a number line. That's what I'm getting. And again, if we drew these correctly, then we should be able to grab a ruler and get a rough measurement of where we are supposed to be. So my picture is not to scale, but I can see that I'm beyond the focal point. So if this is 2 centimeters, this is 3 centimeters, and this is some distance beyond that. So I'm not quite to scale on this picture, but we'll practice a couple where we are to scale so that we can see that as well. Okay, so from here we're just going to start doing some independent practice, trying to draw these rules and match them up, and then working on getting some measurements and working through that equation that we have. Hopefully this was helpful. Please let me know if you have any questions. Thank you.